Hi everyone, let's do a review on chain analysis. The scope of the final exam will include the first order chain analysis. So let's do a quick review. So first is to look at the charge and discharge of an RC circuit. So we derived this before. So for a capacitor, it is driven by current. So we have this ICT, this IT equals C times dVct dt. And then so the switch is initially open and it closes at when t equals 0. So from KVS, we have minus start from the bottom left, minus Vs plus RIT plus VCT equals 0. And we replace IT with C dVct dt. And then you could receive a first order ODE. This is a first order ODE. First ODE. And then solution includes a general complementary solution and specific it's called particular solution, VS particular solution, and this is complementary solution. Okay, so and when plugging the initial condition, so if the initial condition of this capacitor VC0 is 0, the initial voltage of the capacitor is 0, and we are able to find K equals minus Vs. So when charging a capacitor, we could have a formula to represent the voltage of a capacitor, which is Vs times 1 minus e to the power of minus t over tau. And tau is RC. Tau is a time constant equals RC. So please memorize this equation, but also at the same time, I also need you to derive this from KVL, because for this formula only fits when initial condition is 0. So it's only valid. It's only valid when the initial condition is 0. Okay, so if you are given a problem and then initial condition is not 0, then you need to try to lay out the KVL equation and try to find a general solution of V of S, and then find out the value of K. Okay, so we will talk about an example later. So please memorize this equation, and also you have to know how to derive this general solution. Okay. And so we just reviewed the charge of a capacitor, and right now it is the discharge of a capacitor. So for discharge a capacitor, we connect to a capacitor with a resistor. And so we assume that there's an so follows here. You could think of once it is fully charged, and then we connect to a resistor, and then just become this part. We just connect. We just break its connection with the source and connect to the resistor, and so it becomes like this. And one thing you need to be you need to pay attention is, if we assume the current flow is like this, I of t, because when we define the voltage and current of a capacitor, we always define like this. So this is a capacitor, its voltage is positive on the top, negative on the bottom, is VCT. And we define the current flowing through this capacitor, we call it ICT, and the direction is from top to bottom. So if we define the polarities like this, and then we have this ICT equals C divisity dt. We have this equation for a voltage and current relationship for a capacitor. But in this case, if you can notice that the direction of current is from bottom to up. So from the negative side to a positive side, which means the IT here, this current voltage relationship for the capacitor we must put a minus sign here, because right now actually the current we define the current flowing in the opposite direction. So again, so if the current is defined in this direction, then this is positive, this is negative. Okay, so again applied KVL, and we start from the left bottom. It's minus VC plus IT times R. Okay, and you replace IT with this minus C divisity dt equals 0, and then multiply by positive 1, and then divided by RC, you have this divisity dt plus 1 over RC VCT equals 0. And same thing here. This is the first order ODE, and and it's homogeneous. It doesn't have a constant on the right side of the equation. So the general solution is this. And then if we know the initial state, which is the voltage of the capacitor, and then so if initial voltage is VI, then T equals 0, and this whole term is 1, and which means K equals VI. So this is the discharge equation for a capacitor, and so it's tau equals RC. Okay, so please memorize this. Please memorize this equation. Okay, and then we are going to review the discharge of an RL signal. So this switch is initially closed. So if this is closed, the current will all flow into this branch. And then when T equals 0, it is open, means the current will flow in this direction when T is larger than 0. And you also flow into this, we call this IR. And then so we could apply KCL at node A. Let's say this is node A. So we have current flowing into A equals the current flowing out from A. And the inductor is driven by current. So for the inductor equation, it is like this. You have dILT dt times L equals VLT. So you have ILT, IS equals ILT plus IRT. Let's say this IRT. And IRT equals VLT divided by R. So this is IRT. Okay. And so we replace VL by L times dLT dt, and then divided by L over R. So this is our equation. And we have complementary solution and particular solution. And so if the initial condition is 0, and then K equals minus IS, and then we got this. The current of an inductor equals Is, the current source, times 1 minus e to the power of minus t over tau, and tau equals L over R. So please memorize this. And the same thing, this equation is only valid when the initial condition is 0. So when IC is 0, is valid when initial condition is 0. If it is not valid, if the initial condition, if the initial current of an inductor is not 0, then you need to find a way. You need to know how to derive this. You need to know how to derive the general solution of ILT, and then you put into the initial condition and then calculate the result. So if you are still unfamiliar with this, please go back to our notes. We have a full proof of this. And so for discharge of an inductor, and so we apply KVL. So we define currents flowing downward, and then which means current flowing through R, this is positive, this is negative. So starting from the left bottom, so we have minus VL minus R times ILT equals 0. And then since we have this VLT for inductor equals L ILT dt. So replace VLT by L times DLT dt. And then the same procedure, you can find a general solution of this. And then if the initial condition is II, then we put initial current into this equation, and we got K equals II and tau equals L over R. So this is the discharge of an inductor. So please memorize this. Okay, so yeah, so this one is easy. And then after the quick review, let's look at an example here. This example says, assume that the circuit is in steady state with the switch closed prior to t equals 0. And find expressions for the current IT and the voltage VT. So this is IT, ILT. How about let's say it's ILT. So wait, ILT. Okay. Well, we know it's ILT. So it's ILT. And the voltage VT, VLT. Okay. VLT. Okay, first, because the switch is initially closed, so which means it is in steady state. So for steady state, the inductor functions as a short circuit. So the current, so for steady state, it will be like this: positive, negative, Vs, R1, and it is become a short circuit. So I of t equals Vs divided by R1. And the voltage across this is just a wire, so voltage is 0. So when t is smaller than 0, and the current flowing through the inductor is Vs divided by R1. And the voltage across the inductor is 0 because it is a short circuit. Okay, but and then after t is 0 and the switch becomes open and it becomes discharge. This is R2, this is positive minus VLT. We have this ILT, it becomes a discharge mode. So this is discharge. So T is smaller than 0. When T is larger than or equal to 0, this is discharge. Okay, and so it is discharged. How about let's say this. I want to draw it here. So I draw it here. So it is discharged. And it will be better. R2, this is L, positive negative VLT. So during discharge, its initial condition of the current. So we have I 0. It is the same as the previous steady state, Vs divided by R1. Okay, so you have this it's called IT, ILT. Okay, so in this case, because the initial condition is not 0, you have to derive this first order ODE by using KVL. Okay, so this is how it works. So if the current is flowing from positive terminal to negative terminal, and then current flowing through R2, so this is positive, this is negative, and then we can apply KVL. We start from the bottom left, so we meet minus VL minus R2 times ILT equals 0, and VL can be replaced by these equations of an inductor replaced by L times DLT dt. So we have this general solution, right? And tau is L over R2. And because the initial condition is not 0, we cannot apply the previous formula. So we can only derive K by using the initial condition of IL0. So IL0 is Vs over R1, and we have K equals Vs over R1. So this is the general equation for the inductor current. Okay, so this is one of the solution. And it asks you this problem asks you to find the expression for the currents and also the voltage. And so once you find out the current, it should be VLT. Once you find out the inductor current, then by using this equation, you are able to calculate the inductor voltage. So VLT equals L times DLT dt. So it's the first derivative of IL with respect to time. So since IL equals this, so we keep this the same, and then we put the power down here. It's minus 1 over tau, and then this exponential term remains the same. So this is what we have here, and tau equals L over R2. So this is our solution. So for this first order RL and RC circuit, if the initial condition is 0, and then you can apply the formula directly during charge. And if it is not, and then you need to derive the first order differential equation. And for discharge, because you need to find out the initial current first. So once you find out the initial current first, this could be II, right? This is II in the previous formula. Once you find out the initial current, and then you are able to write the formula or to write the equation of the inductor current during discharge. Okay, so this is the current and this is the voltage of the inductor. So this is the answer of this example. Okay, for second order problem, we will review it on Friday's class. And then next problem, I'm going to review the AC steady state analysis. Okay, so for example, find VCT. VCT is the voltage across the capacitor in steady state. Find the phasor current. Find the phasor current through each element and construct a phasor diagram showing the currents and the source voltage. So we need to find phasor current. So we have this through each element. Okay, so first you are given this and you need to convert everything into phasor representation and impedance. And since the source is given by a sine function, so we need to perform this cosine sine conversion. So we talk about this. So we always start from cosine. Cosine theta minus 90 degree equals sine theta. And then we put 1000 t, we replace this theta with 1000 t. So we have this 10 sine 1000 t equals 10 times cosine 1000 t minus 90 degree. So once we convert to cosine, it's the phasor representation of the source of the voltage source is 10 minus 90 degree. Okay, and then for the resistor, its impedance is just a real number, so it's 100 ohm. 100 ohm, and the impedance of an inductor, we use this formula. We derived this before, so right now I just use it. ZL equals omega L J. Okay, and omega is the radius frequency, and since it's given to us, what inside the sine is radius frequency. So it's 1000 multiplied by 0.1 Henry, and it's 100 J ohm. Okay, so we just calculate the impedance of the inductor and write it here. Same thing here, we want to convert this capacitance into its corresponding impedance. So we apply this formula. The impedance of a capacitor equals 1 over J omega C, and also equals minus J divided by omega C. So you just need to multiply the numerator and denominator by J, and you got this. And so minus J divided by 1000 times 10 times 10 to the power of minus 6. So we got minus J 100 ohm. So this is the corresponding impedance for the capacitor. And then, so find a phasor current through each element. So we need to find I first, right? We have 3 currents. So we find I first. So to find I, since we have the source, we need to find an equivalent impedance for these 3. For these resistor and capacitor. And the way to do it is I calculate the parallel impedance for these 2, for the resistor and the capacitor. So I calculate, so its equivalent resistance is called ZRC. It is the parallel of ZZ with ZR. So by using it follows the how to calculate two parallel resistors, right? So ZR multiplied by ZC divided by ZR plus ZC, and then you, so for the division of phasors, we need to convert it to polar form. And once you convert to polar form, you could calculate this is 10 to the power of 4 divided by 10 to the power of 2, and also divided by square root of 2. This is the magnitude. And minus 90 minus 45 degree, and it becomes minus 45 degree ohm. So this is the equivalent impedance for C and R. Okay, and so since we have this equivalent impedance, so we have this. So this is L. This is the equivalent. Let's say this is ZRC. We have ZL, and we have a voltage source, and here it should be AC. Let me take a, and then so Vs equals 10 to the power of minus 90 degree. Okay, so if you want to find out the current flowing through, or we can say flowing out. If we want to find the current flowing out from the source, and okay, wait, we calculate phasor currents, construct a phasor diagram. Construct phasor diagram. Oh, we need to find VCT first. Okay, so VCT is defined by this. This is positive, negative, VC. So we are all work on phasors. So VC can be calculated by using IS and with voltage division rule. So this is voltage division rule. So the top is ZRC. This is ZRC, and the denominator is ZL plus ZRC. Okay, and since we just calculate ZRC is as 70.71 degree minus 45 degree, and then we need to do the summation of this complex number. We need to convert it to rectangular form. So I convert this I convert this polar form into its corresponding rectangular form. And so this is 50 minus 50J. And then because there are phasor multiplication and there are phasor division here, so we need to add this with this and calculate its corresponding polar form. Okay, so this is what I do. I convert everything to polar form, and then we can multiply and subtract and divide. So we have 10 times 70.71 divided by 50 times square root 2, and the angle is phase angle is minus 90 minus 45, because the multiplication is the summation of its phase angles, and then minus 45. Okay, so the answer is 10, and degree is minus 180 degree. Okay, so VCT, so we calculate the phasor representation of VCT, and which is this, and then we could, so this is its phasor, and then we could write down its corresponding time response. Okay, which is 10 times cosine 1000t minus 180 degree. So this is done by voltage division rule. Okay, so this is the first part. It asks us to find VC, and And the second part, it asks you to find the phasor current through each element. Okay, so the phasor current flowing through this L is I, right? So what we have here, okay, to calculate I, we need to calculate the equivalent circuit for these three, right? Because once we calculate the equivalent impedance, we say equivalent impedance for these three, and I equals Vs, the impedance, the phasor of Vs divided by the impedance of the equivalent circuit, and then we can have I. And this I is the current flowing through the inductor. Okay, so let's try this. So we have this, okay, phasor current. Let me see. Hey, so the total impedance of everything, first we calculate total impedance. We call it Z total. So the total impedance equals the ZL plus ZRC, because the inductor and the equivalent impedance of RC, they are in series. So we just sum up their impedance. And to add impedance, we need to convert it from polar form to rectangular form. And then, so this is the result. This is the impedance of the so this is the total impedance. And what's next? So we can, once we find out total impedance, and then we can find out I. So this current, so we can find out I. I is the current flowing out from the source. So I equals the phasor of Vs divided by the total impedance. So I is the phasor of Vs divided by the total impedance of the circuit. So you need to convert everything to its corresponding polar form, and then you can calculate the result. Okay, and so this is the current flowing through the inductor. Let's go back to book. This is a current here. This is a current flowing through the inductor. So you can say this is a current which flowing out from the voltage source. Okay, so and yes, and then we want to calculate, because it also wants us to calculate the phasor currents of IR and IC, and because we know VCT, right? Because we apply voltage division rule in the very beginning. We find VCT. So once we find VCT, VCT is the voltage across this parallel configuration. So IR equals VCT divided by 100, and IC equals so IC equals I minus IR, or IC equals IC equals VCT divided by ZC, because right now we just see this as an impedance. Okay, so we see this as impedance, So IR equals VC, the phasor of VC divided by R. IC equals the phasor of VC divided by the phasor of C, the phasor of this capacitor. So yeah, so this is so we have this, and we have this, and we have this. And if we draw this I, because it needs to satisfy KCL, so we still have I equals IR plus IC. I write it down in the previous page. So we have this, So we have this, we have I, the face of I equals the face of IR plus the face of IC. Okay, so we have this, and then you could double check our result. So we have this, I equals IR plus IC. Okay, it can, because it's a complex number, because it's representing phasor, we need to draw them in the phasor diagram. So phasor diagram is here. So this is I. Yeah, this is I, because I is 0.14. So I is 0.1414 degree minus 135 degrees. So this is I, and IR equals 0.1. Angle is minus 180. So this is IR, and IC. The phase of IC equals 0.1 minus 90 degree, which is IC here. So we have this I, the phasor of the current, equals the phasor of resistor current plus the phasor of capacitor current. Okay, so we find out, by doing this, we find out the current flowing through each component. So we find VCT, and we also find the current flowing through each component. Okay, in the next example, let's look at this. Okay, so it follows the previous example. It computes the power and reactive power taken from the source, and also compute the power and reactive power delivered to each element. So to compute the power and reactive power from the source, we need to know this phasor voltage, phasor source voltage, and then we need to calculate. Actually, we did that previously. We calculated the total impedance of this circuit, and then apply. So this is V C total, and then we apply Ohm's law. We can find out its current. Okay, and so after we find out its phasor current, and then because this is amplitude, we have, if we want to calculate the IMS value, we need to divide it by square root of 2. Okay, so this is amplitude, we divide it by square root of 2, and they become 7.071 volts, and IMS becomes 0.1 amp. And it's phase difference, because when we calculate the this so-called power triangle, we need to also have the phase of this voltage and current. So, and we usually use the phase angle of the voltage minus the phase angle of the current. So it becomes minus 90 minus 135 degree, which is 45 degree. So we have our theta. And so since you find out the VIMS, IMS, and theta, and then you are able to calculate the apparent power, true power, and reactive power. So apparent power is just VIMS times IMS, and the unit is VA. And the true power is VIMS times IMS times cosine theta, which is 0.5 watt. And remember, this unit are different. Okay, and so how about the real power? How about the apparent? Oh, easy. Is wrong. APPARENT. Apparent power. And how about the reactive power? Reactive power is VIMS times IMS times sine theta. So this is the reactive power, and the unit is VAR. Okay, and in this problem, it also asks you to compute the power and reactive power delivered to each element. Okay, so in this case, if we find out I and the power delivered to this inductor impedance is just I squared times ZL, right? So if we use IMS, then this formula is exactly the same as Ohm's law. So if we apply RMS here, so since VR we have the VR we have is VR here. This is amplitude, not IMS value. So this is amplitude of a phasor, not IMS value, but we need to convert it to IMS value. So we divide it by square root of 2, multiply by 100, because the resistor always consumes energy. So I squared R equals 0.5 watt. This is the real power. Okay. And if we want to calculate the reactive power delivered to its load, then we need to find out the current flowing through a load. So we have, so we find out the current flowing through the inductor, which is I. Okay, so which is I. So let's go back. So real power divided to R. So we have this IL IMS square multiplied by ZL. So ZL is 100J, and then IMS, because I is what? We already calculate IMS here is 0.1 amp. So IMS 0.1 squared multiplied by 100J. Even though it has a J here, but when we write down the reactive power, we just say it is 1 VAR. Okay, and reactive power delivered to C. Let's see. We apply the same concept, the reactive power delivered to C, which means IC squared multiplied by the impedance of the capacitor. So let's see. Okay, so we have IC IMS squared multiplied by ZL, and ZL is so this is minus 0.5 J and equals minus 0.5 VAR. Okay, so this is the reactive power of the, no, we have, do we have, yes, we have minus. This is the reactive power of this of C. Okay, so so we finish our review. So for these problems, for the transient, first order transient, and then AC steady state analysis of the circuit. So please review them, and they will be in the final exam.